The manufacture of integrated circuit boards is a complicated, multi-stage process. On completion, many boards will be faulty, but rigorous and complete testing is frequently difficult and uneconomic. In situations like this, a manufacturer must be aware of the implications of cost and uncertainty. He requires a statistical approach. A university statistician who has worked with such problems is Vic Barnett, Professor of Statistics at the University of Sheffield. Vic, is it really important for these companies to tackle their problems statistically? Can't they just use their own judgment?
Well, their intuition might take them a certain way. But in problems of this type, a stage must come when they have to use statistical method to take account of uncertainties, costs, consequences, and so on.
Are the methods straightforward enough to be readily understood by management?
It's important in any cooperation between a consultant and a company that the company understands what it's being told. And of course, well-chosen diagrammatic aids can help with this.
Let's illustrate what Vic has in mind by looking at a dramatisation involving the manufacture and supply of circuit boards like this. I want you to imagine a small microelectronics firm who are considering manufacturing such items and are going to use Vic as a consultant.
Can we have a look at this approach from Hydromat regarding meeting their specification for a new circuit board for their washing machines? Alan, have you got a rough cost breakdown for us?
Yeah, I've looked at it pretty thoroughly. And I estimate that we can make the board for £15 per board.
15.
And I think £35 is a fair asking price. And Hydromat pretty happy with that.
So we're okay on costing then?
Well, there is one slight problem. They do insist at that price on a penalty of £12 for every board they fit, which proves to be faulty. So what we're talking about is a profit of £20 for every good board that we make. But if we supply a faulty board, we lose our initial £15 outlay, plus the £12 penalty, making a loss of £27. So that's the basis on which we go ahead. And we do have to consider it's a market we want to get into.
Yes. What about the failures?
Well, as far as failure rate goes, that's your province, Clive.
Yes, well, I have to estimate a failure rate. On past experience in this area, I would suggest that our failure rate would not exceed 30%.
30%? OK, well, working on that basis, what would that give us as an average profit per board?
Average profit per board? Well, that's a 30% failure rate. That means we have a 70% success rate at £20 profit per good board. That's £14 on average. So with my 30% failure rate at a loss of £27?
Yeah.
3 27s is 81. That's £8.10 from £14 leaves us with, on average, a profit of £5.90 per board, which is reasonable.
Yes, it is, if we can hold it within the 30% failure rate. But what happens if we go over that? And what happens if we go way over that?
Well, as I say, on past experience, I shouldn't expect us to waver much.
But if we do, we get our fingers burnt.
Well, if you're really worried, John, I suggest we call in our consultant. I'll give Vic Barnett at Sheffield University a ring.
Vic Barnett? Oh, hello, Clive. How are you? Yes, well, tell me something about it. New circuit board. Production cost? £15 per board. And selling price? £35 per board. That sounds good. Penalty charge? Oh dear. £12 per board for each faulty item supplied. That's a worry. Well, hold on a moment. Let's just have a look at that structure. Each board may be okay or at fault. We may choose to supply or withhold. Now, if we supply an acceptable one, then we make a profit of £20. Whereas if we supply a faulty one, we lose £27, the £15 manufacturing cost, and the £12 penalty. Of course, we lose a straight £15 irrespective of quality if we don't supply. Now, have you got any way of testing these boards individually? Oh dear. Well, what do you know about the general quality of production? What proportion do you think will be acceptable? About 70%. All right, well, let's suppose for the moment we don't know that. We'll take an arbitrary value, denote it P, and see what is implied. If a proportion of the production P is acceptable, then we're going to make a profit of 20 times P for the acceptable ones and lose 27 times 1 minus P for a faulty item. And of course you want this to be greater than 0 if you're to be in profit. So this means that P has to be at least 27 over 47. Hold on a moment. So that gives us a value of 0.57. In other words, as long as 57% or more of the production run is acceptable, then it looks as if you're on the right side. But you really do have to give some thought to whether you can get a better fix on, firstly, the quality of the production run, but more particularly, can't you find some way of trying to test these items individually before you decide whether to supply them or not?
Let's now return to the boardroom to see what progress has been made after a few months' production.
Since we're what now? 3 months into production of these new circuit boards for Hydromat, I thought it might be worth us taking a brief assessment of the situation. Clive, are you able to give us a progress report?
Yes, well, production's going very well indeed. I'm very happy with it. My original estimate of 30% failure rate has proven to be too high. We're in fact at the moment running on a failure rate of 27%, which is encouraging.
27%. What about Vic's idea that we get the boards tested before they go out to Hydromat? Anybody picked up on that?
Well, Alan and I have both looked into it, and quite honestly, John, it just doesn't seem viable for our operation to test ourselves. However, I have visited a firm and they are willing to carry out the testing. But they will only do this at a charge of a fixed fee per board, which we will have to agree with them, and of course, we would presumably only send out those boards which pass the test. I've seen their operation, and they seem pretty efficient and perfectly capable of setting up the testing system for us. However, they're not totally successful in determining which boards are faulty. They do guarantee a reliability of 95%, faulty or not.
Can you clarify what they mean by this reliability?
Basically, of all boards tested, a few will slip through the net. A small percentage of those that they say are okay will prove to be faulty, and vice versa.
What we really have to decide is it worth having them tested? Because at the moment, we still haven't agreed on the price. Now, if that price proves too high, it's not worth us paying it. We may as well go on supplying them at a 27% fault rate.
And pay the penalty?
Yeah.
Anyway, look, I've given the figures to Vic Barnett, so hopefully he'll come back with a result and give us his opinion as whether we should test or not.
Good.
Now, what Vic is doing is constructing a decision tree, which, when followed from left to right, is a pictorial representation of a sequence of actions and events. He starts with a possible action. His choice of action is to continue supplying the boards without testing or to have them tested. If he does have them tested, we have a possible event. Notice that we use squares for actions and circles for events. Like an action fork, an event fork gives possible paths, but this time we can't choose. Which path we take depends on chance. Either the board passes the test or it fails. Whether it passes or fails, we again have a choice of actions. We either supply the customer or we don't. Of course, we have this course of action if we don't test. That is, either supply or don't. The next possible event will apply whichever path we take through the tree. Either the board is okay or it's faulty. And again, these are all event forks because we can't choose. It depends on chance. Having drawn the tree, The next step is to put in the financial consequences of finishing at each of the ends of the branches on the right. Let's do this one. It costs us £15 to manufacture. But when we deliver, we gain £35. So that's a net £20. If the board is good, that's our profit. But suppose the board is faulty. Then we must refund the £35 and pay a £12 penalty. So we make a net loss of £27. Of course, if we didn't supply the board, we would just lose the manufacturing cost of £15. Now then, what difference does it make if we do test? Well, it's just the same, except that we must be sure to count the cost of testing the individual board. That's a profit of minus T. And of course, it's easy to fill in the rest of the financial consequences. All that remains to do now is put in probabilities and do some calculations. Let's see how this goes by looking at part of the tree we know all about. This is the bit representing no test, and we know that the board is OK with probability 0.73 and faulty with probability 0.27. Now we can work back to the action fork by using these probabilities to calculate the expected gain or loss. 0.73 times 20 plus 0.27 times minus 27, which is 7.31. And what we do is replace the whole event fork by the equivalent value 7.31. We can easily do the same for the next event fork. It's just minus 15. Now we can decide upon our action. An expected profit of £7.31 versus a loss of £15. So our action is obvious. And this is the technique we use for the entire tree. Let's pick up the story at this point with Vic presenting his results to the directors.
The important thing is that we start at this end of the tree with the cost information. And T here, of course, is just the cost of testing an item. We then work our way back through the tree to see the implications. Let's start at this point here, where the rounded probabilities that an item is OK or faulty are 0.98 and 0.02.
Sorry, Vic, I'm not clear about these figures 0.98 and 0.02. I thought we were still dealing with 73% OK and 27% faulty.
Yes, you're right, but remember, we've reached this stage by having first of all tested the item, that the item has passed the test at this stage, and these probabilities therefore have to be the conditional probabilities on the item passing the test.
Let's leave the meeting for the time being while we pick up this point in more detail. The probabilities the managing director has asked about are the probability that it's OK given that it's passed the test. Vic's got that as about 0.98, and the probability that it's faulty, given that it's passed the test. Now, let's see how he arrived at these figures. He knows that the test is 95% reliable. Either the board is OK, we'll call that event B1, or it's faulty and we'll call that event B2. By a reliability of 95%, we mean we know the probability that it passes, given that we know whether it's OK or faulty. Given that it's OK, the event B1, the probability of it passing is 0.95. And that means the probability of failing is 0.05. And we also know that a faulty board will fail with probability 0.95 and pass with probability 0.05. Now, Vic was able to use these figures to obtain the conditional probabilities he wanted by using Bayes' theorem. Let's work one out. The probability of B1 given that it's passed equals the probability of a pass given B1 times the probability of B1 over the probability of a pass given B1 times the probability of B1 plus the probability of a pass given B2 times the probability of B2. Well, the probability of a pass given B1, that's our 0.95 from the table, times the probability of B1, that's one we've always known, 0.73, and that's over, the first term is the same as the numerator, plus the second term is the probability of a pass given B2, 0.05, times the probability of B2, which we know to be 0.27. And if you work that out, you'll get 0.9809. In other words, 0.98 to 2 decimal places. And the rest of them are worked out in exactly the same way.
And finally, we obtain the values 0.12 and 0.88. We now have to consider the profit and loss implications of these results. Again, consider this point here, where an item has passed the test. If we supply it, it might be OK or faulty with respective probabilities 0.98 and 0.02, and returns 20 minus t with probability 0.98, or a return of minus 27 minus t with probability 0.02. The overall effect is an average return 1910 minus t. In exactly the same way, for an item that has passed the test but is not supplied, the average return is found to be minus 15 minus t. For an item which fails but is supplied, the return is minus 21.14 minus t, and for an item which fails and is not supplied, again minus 15 minus t. Now, what are the implications? Well, here, for an item that has passed the test, the return is higher if we supply it. So clearly that's the policy we should adopt. For an item that has failed the test, we obtain a lower loss if we do not supply it. So the overall policy is the intuitively obvious one that we supply or do not supply depending on whether the item has passed or failed the test. But the question now is, should we test? Is it worthwhile from the cost point of view? We have now to take into account these probabilities 0.71 and 0.29 that an item passes or fails the test.
0.71 and 0.29. Let's see how he got those. First, 0.71, the probability that the board passes the test. Now remember, what he knows is the probability that it passes given the board is OK, or as we denoted it, given B1. He knows that's 0.95. And the probability that it passes given B2. He knows that's 0.05. So he can get the probability that it passes by using the theorem of total probability, which says that the probability that it passes is equal to the probability that it passes given B1 times the probability of B1 plus the probability that it passes given B2 times the probability of B2. We know the probability of B1. That's the probability that the board is OK, 0.73. And we know the probability of B2. That's 0.27. So the probability that it passes is 0.95 times 0.73 plus 0.05 times 0.27. And that comes to 0.7070. In other words, approximately 0.71. And of course, if the probability that it passes is 0.71, then the probability that it fails is 0.29.
And so we have these approximate probabilities of 0.71 of passing the test and 0.29 of failing the test. And we can now consider the cost implications of using the test. With probability 0.71, we will have a return of 19.10 minus t. With probability 0.29, a return of minus 15 minus t. The overall effect is an expected return of 9.11 minus t. Now that's interesting because if we compare the 911, apart from the test cost, with the 731, we see that if the test could be done for less than 180, then it must be sensible to use it. Of course, if you could obtain a more reliable test, that could be even better.
OK, so that's fine. And it all worked out in the end because they were able to negotiate a fee of 70 pence per test. So they were doing nicely and everybody was happy. But it's important to realise that situations such as this are not static. Modifications develop, and when they do develop, can they be incorporated into this kind of a structure? Let's eavesdrop on another meeting in this same boardroom a couple of months later.
Well, Vic, things are now going very smoothly with Hydromat. We're all very grateful for your help on this one.
Well, I was very pleased to be able to help. Let me know if there's anything more I can do on it. With no test, the return was 7.31 per item on average. With the present test and the present test fee of 70p, the return is 8.41. Now, what happens with the new test? Well, an item may pass the test, and 73% will indeed do so. Or it may be judged faulty, 27% will be faulty. The returns will be 20 minus S, say, the cost of the new test in this case, and minus 15 minus S here. Of course, this is not minus 27 because the £12 penalty fee now doesn't have to be paid since you're not going to deliver faulty boards. So the overall position then is 0.73 times 20 minus S is 14.60 minus 0.73S. 0.27 times minus 15 minus S is minus 405 minus 0.27S. So overall the position to compare with these is 10.55 minus S. Now that's interesting. Compare it with 8.41. As long as you could negotiate this new test for less than about £2.14p, then you're in business, and I would have thought the company would be most interested to negotiate at that level.
Splendid, thank you.
Well, of course, we've had to simplify some features in the dramatisation you've just seen, but not inordinately so. A real problem would have a more complicated decision structure, but the techniques would be just the same and would produce useful, quick answers. We hope you've seen that quite straightforward statistical methods can profitably be used to solve quite complicated problems.